In this lecture, we are going to discuss now the concept of probability. So what's the meaning of a probability? And then we will discuss a special type of probability, which is the conditional probability. The material is still part of chapter 2 of your textbook, and these are the topics that we are going to discuss. So we will talk about how do we understand probability, what does it mean, the term probability. Then we will discuss one important rule which is used to calculate the probability of joint events, and then we will discuss a situation where we have the conditional probability, which is a special type of probability calculation. Now, the term probability is basically used to quantify the likelihood of an occurrence of a particular outcome or a particular event. And there are different ways to interpret that term. There is like the general degree of belief interpretation. So when I say that there is a 30% chance that it's going to rain today, it's kind of just a feeling or a representation of a feeling, the representation of likelihood through feelings, but this will differ from one person to the other. But what we are more concerned about, or what we really care about in this course, is the kind of more scientifically and mathematically rigorous definition, which is based on what's called the relative frequency. So the probability of a particular outcome is the proportion of times the outcome occurs out of n repetitions as n increases to a very large number. So mathematically, it's the number of occurrences divided by the total number of trials as the number of trials goes to infinity. Again, it's kind of just a theoretical math representation, but the idea is that it depends on the relative number of repetitions. That's basically what the probability means, or the representation of likelihood through formal probability definition means. Now, some conventions, this number has to be between 0 and 1, just by convention and definition, and the higher the number, the more the likelihood that you are trying to represent. And if the number is 0, it means that the event will never occur, or the outcome will never occur. So it's an impossible outcome. And if the probability or the number is equal to 1, it means that every time I repeat the experiment, this outcome will keep on occurring. So the experiment becomes no longer probabilistic or random, and it becomes almost a deterministic. Now, in order to be able to calculate probabilities, there are certain kind of general logical assumptions and beliefs. Okay, so whenever I have a sample space of n possible outcomes, and my knowledge of these outcomes says that there is no reason for one of them to occur more frequently than the others, then in this case those outcomes are called equally likely, and the probability of each one of them is equal to 1 divided by the total number of items in the sample space, right? So if n is the number of outcomes, then the probability of each one of those equally likely is going to be 1 over n. Another important thing is, how can I calculate the probability of an event? Well, again, by definition, an event occurs when any one of the outcomes of that event occurs, right? So an event, as we mentioned, is a subset of the sample space, right? Subset of outcomes from the sample space. So if this event E includes the subset of those 4 possible outcomes out of all the outcomes in the sample space, right? Then I would say event E occurred if any one of these occurs. So if this or this or this or this occurs. And we know by definition that an occurrence of one outcome in the sample space means that all the others did not occur. So simply out of these two logical findings, we can easily define the probability of an event as the sum of the probabilities of the outcomes inside the event. So in this case, I have to add the probabilities of those 4 outcomes that compose the event, and that will give me the probability of the event P of E. Okay. Here is an example that shows how to calculate the probability of a particular event. So assume that a random experiment has this sample space, so the possible outcomes are A, B, C, and D. These outcomes are not equally likely, but in this case they have particular probabilities. So these are the probabilities of the different outcomes. And assume that event A is defined as the occurrence of the outcome A or B, right? So if A or B occurs, this means that event A occurs. And event B is defined as the occurrence of B, C, or D, right? Last, event C occurs when outcome D is the outcome of the experiment, okay? If you want to calculate the probability of A, it's simply the sum of those 2 probabilities, the probabilities of outcome A and the probabilities of outcome B. This is outcome A probability and this is outcome B probability, so that probability of event A becomes 0.4. Similarly, you can pause the video here and watch the remaining calculations. They are all dependent on the same thing, that a particular event, even if this event is defined as a joint or a combination of the events using intersection or union or whatever, right? The probability of this super event, which is the combination of those 2 in a particular way, is the sum of the probabilities of the outcomes listed in this set, right? So again, it's the probability of B. Now, any theorem in math is built on axioms. Axioms are logical facts, logical findings that do not require any mathematical proof, and you cannot actually prove them. They are like your start point of proving. So the axioms of the probability theory are very simple. There are only 3 axioms to the probability theory. Some people argue actually that the third is not an axiom, but anyways, as far as we are concerned here, those 3 that you see here are the axioms of the probability theory. That, number 1, by definition, the probability of the sample space is equal to 1. Again, sample space will always occur, because the sample space is the set of all possible outcomes. And when you do the experiment, one of those possible outcomes is surely gonna be your output, right? Either one of them, any one of them as an outcome will mean that the sample space occurred. So the probability of the sample space must be equal to 1. The second is that the probability of any event, the probability in general, is greater than or equal to 0 and less than or equal to 1. So it's always a positive number and it's always less than 1, right? And that's again by definition of the probability as a measure of the likelihood. And keep in mind that it's a crime if you do any calculations and then you find the calculation of the probability for a particular event or a particular outcome is something greater than 1 or something negative, and then you leave it as it is. You should at least comment on that situation that you are sure that the results are wrong, and you should not keep it that way. Okay. The third is if 2 events, E1 and E2, are mutually exclusive, they don't intersect, they don't have anything common between them, right? Then the probability of the union of those 2 events, right, is equal to the sum of the probabilities of the 2 individual events. Okay. Well, out of these axioms, there are several like important results, such as the probability of the empty set is equal to 0, and the probability of a complement of an event is equal to 1 minus the probability of the event, right? And these can be easily proven from the axioms described up there. Now, another important thing to look at is the situation of joint events, right? Joint events are generally generated by applying set operations to individual events. And in particular, the most important joint events that we're concerned about are the probability of the union of 2 events, the probability of the intersection of 2 events, and the probability of the complement of an event. And let me mark those with different colors so that we can show them easily on the graph. So the intersection of the union of 2 events A and B is basically this set, right? So it's the union of those 2 guys, right? This is the union with the black. and the intersection, which is with the red color, is this guy, right? So this is the intersection of those two events A and B. And the last thing is the complement of A, right? So it's everything outside A, right? So it must be this whole, everything in the sample space except whatever is inside A, right? So this is the complement of A, right? Everything in blue here is the complement of A. Now, what we are trying to do in this part, the joint events, is to find an expression for those joint events or events that are combining two events together with different set operations, right? As a function of the individual probabilities of the events. So that's what we are trying to do. So the first rule which helps us to calculate the probability of joint events is called the addition rule, and the addition rule helps in calculating the probability of the union of two events. Okay, let's look at this example and try to deduce where the addition rule comes from. In this example, we are looking at wafers which are used for just an alloy of silicon which is used to manufacture electronic chips, the electronic ICs, right? And those wafers are typically pure, but they might be contaminated. And there is a tool that can be used to test the wafers to figure out whether they are contaminated or not. And this tool sometimes tests in the middle, sometimes tests at the edge, right? So now we are looking at a set of 940 wafers which are being tested for contamination. Using the tool, 626 of these were tested at the center, while 314 were tested at the edge, right? Now, out of the 940, there are 358 were found with high contamination, and 582 were found with low contamination in the alloy itself, right? Now, if we want to calculate the probability of two different events, the event H, which defines that the wafer is highly contaminated. Now, how many outcomes are in this event? There are 358. And how many total possible outcomes? There are 940. So the probability of H is equal to the division of those two numbers. Similarly, if we define C as the event that the wafer is tested at the center, so how many are falling in this category or in this event? There are 626, and how many total? 940, and the probability of that event is equal to the division of the two numbers, right? Now, if we want to figure out the probability of the union, right, H union C, which means that here is H, right? Here is H, if you want to put it as a set, right? This is H, and here is C, right? If you want to put it as a set. So this is C. And if you want to calculate the probability of the union, so probably what you would do is add those numbers together, which gives you the total number of outcomes in this union, and then you divide that by 940. Now notice that if you want to do this by using those two numbers, right, what you have been doing is this is the sum of this plus this, right? And this is the sum of this plus this. So if you add this one to this one, right, you will end up adding this plus this plus this plus this again. So this is repeated because it's the intersection. But we know that the union is simply the sum of these three numbers only, right? This plus this plus this. So you must subtract the repetition of this, which is basically what we see here, the subtraction of the intersection, because it's added twice, and this is how you can conclude. So basically, this important rule is called the rule of addition, or the addition rule. Now, special cases is if A and B are mutually exclusive, so they don't intersect in the first place, and in this case you can easily figure out that the probability of the union is going to be simply the sum of the probabilities. Will be generalized in the case of events E1 up to EK, and each one of them is mutually exclusive with all the other events. So none of these events intersect. They are all separate from each other. They don't have any intersection. Then the probability of all these events from E1, E2 up to EK, right? the probability of the union of all of these is going to be simply the sum of the probabilities because they are mutually exclusive. Okay. Now the other important notation of probability is the conditional probability. So assume that I'm looking for the probability that event A occurs, and I can calculate that by the calculating the probabilities of the outcomes inside A, or by calculating the number of possible outcomes inside A and how many times they occur, and dividing that by the total number of possible outcomes in the whole sample space in the case of equally likely. Now assume that rather than calculating the probability of A and that's it, which is the unconditional case, the normal case, I'm telling you that event B has occurred, right? And given that this is the case, I want to know what's the probability of occurrence of event A. Now in this case, the situation is a little bit different, right? Because once I tell you that event B has occurred, then this means simply that the sample space has changed, and you know already that B occurred. This means that the possible outcomes is one of the outcomes of B, and then given this information that the set of possible outcomes becomes simply event B, given this information you are trying to figure out what's the probability of A occurring, or vice versa. So assume that I tell you that A occurred and I want to find the probability of B. So this is the conditional probability of event B occurring given that A has occurred. And in this case, A becomes my sample space, right? And given this information, given that this is my sample space, which is currently reduced, what's the probability that B occurs, right? And this must be a different calculation. And in this example, again, we are illustrating how you can calculate this conditional probability. Assume, for example, that I have a manufacturing process which is which produces a certain set of product, and 10% of the parts that are produced from this manufacturing process contain visible surface flows, and 25% of the parts with surface flows are, so basically I have the ones with surface flows which are noted by F, right, which is 10% of the overall production, right? And then out of these 10%, there is a 25%, so it's 25 of the 10%, right, are defective parts, while the remaining ones are not defective. Now, on the other hand, the parts that are with no surface flows, the ones that are fine, they look fine, 5% of them are actually, so this is a 5% of the whole non-defective by looking ones, okay, non-surface flows ones, sorry, okay. Now, if I want to say what's this 25%, the 25% in this case, by definition, by description, is the probability of being defective, given that my sample space is only the ones with surface flows, right? So this 25% is not the probability of being defective. It's just the probability of being defective, given that I fall within these. While the 5% here is the probability of being defective, given that I fall within or conditioned on no surface flows, right? So that tells you how the conditional probability looks like in terms of what does it mean, right? Now in terms of calculation, the conditional probability of B given A is equal to the probability that the intersection between A and B occurs divided by the probability that A has occurred, right? And you can simply figure out by using Venn diagrams why this is the case, and I leave it to you as an exercise. Also, I leave it to you to look at the example given here, where you try to figure out those probabilities by yourself, okay, by pausing the video here and trying to do the calculation. Last is a representation of the conditional probability case that we had in the slide before this one, the slide that had the surface flows and defective ones, with the table that was shown there, right? This shows that there are two possibilities for the surface flows. One of them is that no surface flow, or there is a surface flow, and there were 360 out of 400 with surface flows, so the probability of without surface flows, so probability of no surface flows is the division of those two numbers. On the other side, there were only 40 out of the 400 with visible surface flows, so the probability is 40 divided by 400. Now, whether the first one was with surface flows or without, right? There are possibilities for the second situation, which is being defective or being non-defective. So out of the 40, in this case, my total population becomes the 40, right? Out of the 40 that had visible surface flows, 30 of them were non-defective, while 10 of them were defective, right? So these numbers are the probability of defective given surface flow occurred. And this number is the probability of not defective given surface flow occurred, because I start from a point where the surface flow occurred, right? And then the second case is starting from F bar. So here everything is going to be conditioned on F bar. So this is how you can visualize this in a tree diagram.